Hey, Harsh here. Today we are tackling two foundational yet complex concepts, database replication and leader election. These mechanisms are crucial for guaranteeing data availability, fault tolerance, and improved performance in modern applications. Think of a modern application, whether it is handling billions of financial transactions or serving content worldwide. It simply cannot rely on one machine. Replication solves the issue of data safety by creating redundant copies. If your primary database, often called the master or source, fails, replicas immediately provide uninterrupted data access. Replication works by detecting data changes on the primary, capturing those data changes, transmitting them to the replicas, and applying them in sequence to maintain synchronization. Leader election tackles a related but different problem. Coordination. When multiple nodes are working on shared data or performing complex tasks, you need a single source of truth, the leader, to prevent data corruption, conflicting decisions, or duplicated work. Replication provides data redundancy. Leader election provides operational consistency. A classic replication pattern is master slave. In the configuration, the master server is the source of truth. Any change, an update, a deletion, a new record must occur here. The slaves or replicas hold synchronized copies of data. Why separate them? Because most applications, especially web services, are read heavy. By offloading read traffic to dedicated slave servers, you reduce the load on the master, leading to massive scalability gains for read performance. This model works exceptionally well for scale out solutions, spreading the load amongst multiple slaves to improve overall performance. For instance, if you have 10,000 read queries per second and only 100 write operations, having multiple read replicas significantly boosts throughput. The core mechanism involves the master logging its updates and the slaves confirming they have received and applied them successfully. This is an essential pattern when complexity, such as resolving write conflicts, needs to be minimized. Let's examine the replication handshake. When a write occurs on the master, it's first recorded sequentially. For systems like MariaDB and MySQL, we enable the binary log or log bin and assigned a unique server ID. The format of this log is critical. Row-based logging records that extract data changes giving the highest accuracy, while statement-based logging records, the SQL commands itself. If you use statement formats in MariaDB, you might encounter errors, especially with foreign keys, which is why mixed format is often used to allow replication of complex operations. The slave connects to the master using a dedicated replication user. It then continuously pulls the log data, tracks its position, and stores it locally in a relay log before applying the updates. This relay log acts as a buffer, preventing performance differences between master and slave from causing replication lag to cascade. The multi-threaded application capabilities in modern systems allow parallel processing of transactions, further improving throughput. Replication is more than just a backup plan. It's a strategy for high-performance operations. For disaster recovery, organizations can maintain current data copies in separate cloud regions or facilities, allowing rapid recovery from catastrophic failures. Critical replication allows for intelligent workload versatility. For instance, large database backups traditionally require shutting down the master, but with replication, you can pause the slave and create a clean snapshot of the live data without interrupting production. This is invaluable for maintaining zero downtime. Furthermore, analysis of information, which is often resource intensive, can take place entirely on the slave, ensuring the transactional performance of the master remains completely unaffected. If network load on one single master becomes a bottleneck due to too many slaves, performance can be optimized using a cascading replication structure. Here, the master replicates only one primary slave, and the remaining slaves connect that primary slave for their replication requirements. This strategy effectively spreads the load of distributing the binary log. The key insight here is that replication gives you redundancy and operational flexibility. The most critical design decision in replication is determining your tolerance for consistency versus latency. Synchronization replication ensures that data on the master and slave are always sync, like they have two mirror updates simultaneously. However, this safety comes at a cost. Every write operation must wait for network round trips, impacting application's performance during high volume operations. Asynchronous replication prioritizes speed. The master commits the change locally and then immediately tells the application it's done, querying the change to be written later. This is much faster, but if the master fails before the change reaches the slave, those changes are lost. This is why data consistency can be difficult to maintain, especially in asynchronous situations where data replication may be delayed. Semi-synchronous replication is a middle ground aiming to reduce the risk of data loss while maintaining acceptable performance. Choosing the right configuration is essential. If your application can tolerate slight delays in consistency, asynchronous replication offers significant performance benefits. Let's get practical using MariaDB, a widely used open source relational database. The setup process, which is fully suitable for MySQL databases as well, starts by creating two separate server environments, one for master and one for slave. On the master, we added the config file to set a unique server ID and enable binary logging using logbin. We must create a dedicated replication user with a replication slave privileges. On the slave, we also set a unique server ID. Optionally, in production, you might set slave skip errors equal to all to prevent replication from stopping due to small innocuous errors, but this should be avoided during development. Finally, on the slave, we can use the change master2 command specifying the master host, the application user's credential, and the binary log file and position. Once the slave threads are running, we verify that changes made on the master successfully replicate to the slave. While master slave is excellent for read scalability, scaling the right capacity on the single master is difficult, often required costly vertical scaling. Furthermore, if master fails unexpectedly, manual intervention is typically needed to promote a slave to master status, causing delay. Multi-master replication is a solution for high availability writes and in complex systems. Since changes flow bidirectionally between active nodes, if one node fails, the other can continue processing read and writes. However, the complexity skyrockets when two users try to update the same record on two different masters simultaneously. This creates a data conflict that requires a defined resolution strategy. Because of these conflict complexities, master-slave remains simpler and safer to read-heavy applications. Both models suffer from write amplification, where the cost of single write operation multiplies across replicas. In a distributed environment, resources are shared and operations are concurrent. Without a leader, multiple nodes may try to perform the same critical task like charging a customer twice, which could be disastrous. The leader acts as a coordinator, ensuring exclusive access to shared data and organizing flow. For replicated database systems, the leader is simply the master node which handles all writes to prevent corruption. The election process must be highly robust to handle network outages and process failures. The safety condition of any robust election algorithm is critical. Only one processor is allowed to enter the elected state. If two nodes believe that they are the leader simultaneously, you enter a split brain situation, which is a major concern in system design. The leader election process needs consensus algorithm to decide who holds the power, especially when failures or network partitions occur. Distributed locking is difficult because it cannot rely on simple mutexes across different machines and unreliable networks. Amazon, for example, heavily uses leases for leader election because they are straightforward and provide built-in fault tolerance. A lease works because it depends on only on local elapsed time duration, not on a globally synchronized valve lock, which is crucial in distributed systems. The leader claims the lease by automatically updating a record in a strongly consistent store, like a file in GCS or a record in DynamoDB. Once elected, the leader continually renews this lease via a heartbeat mechanism. If the heartbeat stops because the leader crashed, the lease expires. The remaining nodes detect the expiration and the race to acquire the lock, the first to win becomes the new leader. The biggest challenge here is ensuring that the elected leader only performs work while it holds the lock, guarding against issues like network slowdowns or garbage collection pauses that might cause the system to incorrectly assume it has the leadership. For systems where external coordination services aren't used, custom algorithms are necessary. The bully algorithm is simple. The node with the highest identifier wins, bullying the others into submission. If a node detects a failure, it sends an election message to all nodes with an higher ID. If it receives any OK response, it drops out and waits for I1 message from the higher ID node that took over the election. The worst case scenario occurs when the lowest ID process initiates the election, forcing N processes to initiate elections sequentially, resulting in O of n squared time complexity. In contrast, ring algorithm imposes a logical ring structure. When a node detects failure, it sends a message containing its ID to its successor. Each subsequent node adds its own ID, piggybacks it, and passes the accumulating list along. When the message returns to the initiator scans the list of live nodes and announces the highest ID as the leader. This ensures that only active nodes participate and it requires fewer overall messages than Bully algorithm, making it preferable for time-critical systems if network congestion is managed. When strong consistency across write operations is non-negotiable, for instance, managing transactional data or defining which database log entry is absolutely the truth, we turn to consensus protocols. These protocols are the engine behind most consistent distributed systems. Paxos is the foundational but notoriously complex protocol for reaching consensus. Raft emerged as a more understandable and implementable alternative. Raft organizes nodes into electoral terms. When a follower detects the leader has failed, it becomes a candidate, increments the election term number, and requests votes from other nodes. If it wins a majority, it becomes the new leader. The majority rule is the key. It ensures that during network partitions, only the majority partition can accept writes, preventing conflicting updates and maintaining integrity. These algorithms are generally used internally by specialized coordination services like ZooKeeper, allowing application developers to leverage strong consistency without implementing the complex mathematics themselves. When designing a system, you almost never implement Raft or Paxos directly. Instead, you integrate with a battle-tested coordination service like ZooKeeper, for instance, provides a highly dependable, self-distributed service. For lead election in ZooKeeper, each candidate node creates an ephemeral sequential Z node. Ephemeral means the Z node only exists while the client connection is active. If the leader crashes, the Z node is automatically deleted. Sequential means that the node gets an incremented ID and the node with the smallest ID is automatically elected leader. Other nodes watch the predecessor Z node, ensuring prompt failover. Cloud services offer similar primitives. Azure uses leases on the storage block to implement a shared distributed mutex. The first instance to acquire the lease becomes the leader. This delegates the complex responsibility of atomicity and consistency to the reliable cloud infrastructure. This approach is often the easiest and the most tested way to implement leader election. One significant drawback of single leader is scaling limit. If a leader elected system needs to grow beyond what one server can handle, either in data size or request rate, a complete re-architecture is required. The solution used by industry giants like DynamoDB is sharding. Instead of one monolithic leader, the data is partitioned into non-intersecting and independent replica sets. Each of these partitions or shards operates independently and has its own designated leader. For example, Amazon EBS elects primaries for each area of the volume to order reads and writes, ensuring local consistency without requiring a global coordinator for every operation. This dramatically increases the system's capacity to handle requests and manage data volume, distributing the blast radius of a failure. The challenge here, however, is the increased design complexity required to correctly shard the data and manage the coordination between potentially hundreds of local leaders. The most thorny problem in fault tolerance is dealing with crashing leader. Network partitions and temporary outage make it hard to know if the old leader is truly dead or just isolated and still actively working. If the system incorrectly elects a new leader while the old one is still operating, you have two leaders, split brain, and certain data corruption. The solution often relies on idempotency. By making all the critical operations idempotent, meaning running them twice or more has the same outcome as running them once, the new leader can safely pick up and restart the work that old leader might have left incomplete, mitigating the risk associated with short periods of dual leadership. For critical systems that must have at most one leader, the election mechanism must ensure that the outgoing leader is definitely disposed before the new leader is elected. This is where formal verification tools like TLA Plus are used to mathematically prove the correctness of the distributed algorithm. We have covered a massive amount of ground today, transitioning from fundamental database redundancy to complex logic of distributed consensus. Remember, replication is the safest net that prevents catastrophic data loss and dramatically improves read performance. Lead election is the organizational principle that prevents chaos and ensures consistent state. When designing your next large system, you can ask yourself, can I tolerate eventual consistency async, or do I need immediate safety sync? And how am I coordinating my nodes during a failure? The solution lies in using established protocols like Raft and leveraging modern coordination services to manage those vital distributed logs. This video was a little too complex, I feel like. Hey, if this video helped you understand this topic, don't forget to like and subscribe. You can also drop your suggestions down in the comments about the improvements and the topics you would like me to cover next. Till then, thanks for watching, and I will see you in the next one. Peace.